In electrical systems, understanding the relationship between different voltage levels is crucial. Let's clarify the connection between 120 volts and 208 volts, specifically focusing on which one serves as the base voltage. When dealing with these two voltages, the question arises which is the foundational value from which the other is derived. The correct understanding is that 208 volts is the base voltage. This means that 120 volts is obtained by dividing 208 volts by the square root of 3, which is approximately 1.73. Conversely, 208 volts can be calculated by multiplying 120 volts by 1.73. The base voltage is the reference point for determining the other voltage in the system. To elaborate, consider a three-phase electrical system, often used in commercial and industrial settings. In such a system, three alternating current voltage sources are present, each with the same magnitude but separated by a phase angle of 120 degrees. When these three phases are connected in a Y configuration, a neutral point is created at the center. The voltage between any one of the phases and this neutral point is 120 volts. However, the voltage between any two of the phases is 208 volts. This 208 volts is what we refer to as the base voltage in this context. The relationship between 120 volts and 208 volts is a direct consequence of the geometry of the Y connection and the phase angles between the three phases. The voltage between any two phases is √3, or approximately 1.73 times the voltage between a phase and the neutral. Hence, the formula 208 volts equals 120 volts multiplied by 1.73. Therefore, 208 volts is the fundamental voltage from which 120 volts is derived. Thinking about it another way, if you have a 208 volt three-phase system, you can derive 120 volts from it. But if you only have 120 volts, you would need a transformer to step it up to 208 volts in a three-phase configuration. This makes the 208 volts the origin or base voltage. The concept of base voltage is important for several reasons. Firstly, it helps in understanding the voltage levels in different parts of an electrical system. Secondly, it is essential for calculating current, power, and impedance in the system. Thirdly, it is useful for troubleshooting electrical problems. For instance, if you measure 208 volts between two phases in a three-phase system, you know that the voltage between any phase and the neutral should be approximately 120 volts. If it is significantly different, it could indicate a problem with the system. It's worth noting that while 208 volts is the base voltage in this particular scenario, the term base voltage can also refer to other voltages in different contexts. For example, in a 480/277 volt system, 480 volts would be considered the base voltage. Similarly, in a 240/120 volt single-phase system, 240 volts would be the base voltage. The key is to identify the voltage from which the other voltage is derived. The 208/120 volt system is commonly found in commercial buildings, where both 120 volt outlets for standard appliances and 208 volt circuits for larger equipment are required. For example, you might find 120 volt circuits powering lights and computers, while 208 volt circuits power air conditioners and electric heaters. Understanding the source of these voltages ensures proper and safe installation and operation of electrical equipment. When working with electrical systems, it is always crucial to adhere to safety precautions and local electrical codes. Incorrect wiring or improper use of equipment can lead to electrical shocks, fires, and other hazards. Always consult with a qualified electrician for any electrical work, especially when dealing with unfamiliar voltage levels or wiring configurations. So to summarize, in a 208/120 volt system, 208 volts is the base voltage from which 120 volts is derived by dividing by the square root of 3. This understanding is crucial for the design, installation, and maintenance of electrical systems, as well as for ensuring the safety of people and equipment. Remember that the base voltage is context dependent and can vary depending on the system. The key is to identify the voltage from which the other voltage is derived. To solidify your understanding, consider the following analogy. Imagine you are baking a cake. The recipe calls for 2 cups of flour and 1 cup of sugar. In this analogy, the 2 cups of flour can be considered the base ingredient, as the amount of sugar is determined by the amount of flour. Similarly, in a 208/120 volt system, 208 volts is the base voltage, as the 120 volts is determined by the 208 volts. Now, let's delve a bit deeper into the practical implications of understanding the relationship between 208 volts and 120 volts. Consider a scenario where you're installing a new air conditioner in a commercial building. The air conditioner requires a 208-volt power supply. You check the electrical panel and find that there are several 120-volt circuits available, but no 208-volt circuits. What do? In this situation, you would need to install a new 208-volt circuit from the electrical panel. This would involve running new wires from the panel to the location of the air conditioner and connecting them to a 208-volt breaker. It is crucial to ensure that the wiring is properly sized and rated for the load of the air conditioner, and that all connections are made according to local electrical codes. Alternatively, if the building already has a 208-volt 3-phase power supply for other equipment, you could tap into that supply to power the air conditioner. However, this would require careful planning and coordination to ensure that the existing circuits are not overloaded. In either case, it is essential to consult with a qualified electrician to ensure that the installation is done safely and correctly. Another important consideration is the voltage drop in the wiring. Voltage drop occurs when the voltage at the end of a wire is lower than the voltage at the beginning of the wire. This can happen due to the resistance of the wire, especially over long distances. Voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, it is important to use wires that are properly sized for the load and the distance. You can also use multiple wires in parallel to reduce the resistance. Local electrical codes typically specify the maximum allowable voltage drop for different types of circuits. When designing an electrical system, it is important to consider voltage drop and take steps to minimize it. In summary, understanding the relationship between 208 volts and 120 volts is crucial for a variety of practical applications, from installing new equipment to troubleshooting electrical problems. By mastering this concept, you can ensure the safe and efficient operation of electrical systems in commercial and industrial buildings. Remember to always consult with a qualified electrician for any electrical work, and to adhere to local electrical codes. Let's consider the National Electrical Code, or NEC, which provides guidelines for safe electrical installations. The NEC addresses voltage drop in section 210.19. The NEC recommends that the voltage drop on branch circuits should not exceed 3%, and the voltage drop on feeders should not exceed 5%. A branch circuit is the circuit that runs from the last overcurrent protective device to the outlets. A feeder is the circuit that runs from the service equipment to the branch circuits. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current resistance for the conductor material in ohms per circular millifoot. For copper, K is typically 12.9 ohms per circular millifoot. I is the current in amps, D is the one-way distance in feet, and Cm is the circular mil area of the conductor. Let's look at an example. Suppose you have a 120 volt circuit that is supplying a 15 amp load. The distance from the panel to the load is 100 feet, and you are using number 12 American wire gauge copper wire, which has a circular mil area of 6,530 circular mils. The voltage drop would be calculated as follows: voltage drop equals 2 times 12.9 times 15 times 100 divided by 6,530, which equals approximately 5.9 volts. The percentage voltage drop would be calculated as follows: percentage voltage drop equals voltage drop divided by source voltage times 100. Percentage voltage drop equals 5.9 divided by 120 times 100, which equals approximately 4.9%. Since the percentage voltage drop is less than 3%, the circuit meets the NEC requirements for voltage drop. In addition to voltage drop, the NEC also addresses other aspects of electrical installations, such as wiring methods, overcurrent protection, and grounding. It is important to be familiar with the NEC and to follow its guidelines when working with electrical systems. Understanding the NEC and its requirements is essential for ensuring the safety and reliability of electrical installations. Now, let's consider the different types of electrical systems that utilize 208 volts and 120 volts. The most common type of system is the 208/120 volt three-phase Y system, which we have already discussed. This system is widely used in commercial buildings, as it provides both 120 volts for lighting and small appliances and 208 volts for larger equipment. Another type of system is the 240/120 volt single-phase system. This system is commonly used in residential buildings. In this system, the voltage between the two hot wires is 240 volts, and the voltage between each hot wire and the neutral wire is 120 volts. This system allows for the use of both 120 volt and 240 volt appliances. A third type of system is the 480/277 volt three-phase Y system. This system is commonly used in large industrial facilities. In this system, the voltage between any two phases is 480 volts, and the voltage between any phase and the neutral wire is 277 volts. This system is typically used for powering large motors and other heavy equipment. The choice of electrical system depends on the specific application and the voltage requirements of the equipment being used. It is important to select the appropriate system to ensure safe and efficient operation. When selecting an electrical system, it is also important to consider the available power supply. The power supply must be capable of providing the required voltage and current to the system. It is also important to consider the reliability of the power supply. A backup power supply, such as a generator or an uninterruptible power supply, may be necessary to ensure continuous operation in the event of a power outage. In summary, understanding the different types of electrical systems and their voltage requirements is crucial for selecting the appropriate system for a given application. It is also important to consider the available power supply and its reliability. Let's dive deeper into grounding and bonding in electrical systems. Grounding is the process of connecting electrical equipment to the earth, while bonding is the process of connecting different metal parts of the electrical system together. Grounding and bonding are essential for safety, as they help to prevent electrical shocks and fires. When electrical equipment is properly grounded, any fault current will flow to ground, tripping the circuit breaker or fuse and de-energizing the circuit. This helps to protect people from electrical shocks. Bonding helps to create a low impedance path for fault current, which also helps to trip the circuit breaker or fuse quickly. The NEC provides detailed requirements for grounding and bonding in electrical systems. These requirements cover the size and type of grounding conductors, the methods of connecting to ground, and the bonding of metal parts. It is important to follow the NEC requirements carefully when installing and maintaining electrical systems. Grounding and bonding are critical for safety and should never be overlooked. One of the most common grounding mistakes is improper grounding of equipment. Equipment grounding is the process of connecting the non-current carrying metal parts of electrical equipment to ground. This helps to prevent electrical shocks if the equipment becomes energized due to a fault. The NEC requires that all electrical equipment be properly grounded. Another common grounding mistake is improper bonding of metal parts. Bonding is the process of connecting different metal parts of the electrical system together. This helps to create a low impedance path for fault current. The NEC requires that all metal parts of the electrical system be properly bonded. In addition to grounding and bonding, surge protection is another important aspect of electrical system safety. Surges are sudden increases in voltage that can damage electrical equipment. Surges can be caused by lightning, power outages, or other events. Surge protectors are devices that protect electrical equipment from surges by diverting the excess voltage to ground. The NEC requires that surge protection be provided in certain situations, such as in areas that are prone to lightning strikes. Surge protectors should be installed at the service entrance of the building and at individual pieces of equipment. In summary, grounding, bonding, and surge protection are all important aspects of electrical system safety. By following the NEC requirements and installing appropriate protection devices, you can help to prevent electrical shocks, fires, and equipment damage. Finally, let's address the impact of harmonics on electrical systems. Harmonics are distortions of the sinusoidal waveform of the alternating current. Harmonics can be caused by nonlinear loads such as electronic devices, variable frequency drives, and fluorescent lighting. Harmonics can cause a variety of problems in electrical systems, including overheating of transformers and conductors, increased energy losses, and malfunction of equipment. To mitigate the effects of harmonics, harmonic filters can be used. Harmonic filters are devices that reduce the amplitude of harmonic currents. Harmonic filters can be installed at individual pieces of equipment or at the service entrance of the building. Another way to reduce harmonics is to use equipment that generates fewer harmonics. For example, energy-efficient lighting and variable frequency drives with harmonic mitigation features can help to reduce harmonic distortion. Harmonic analysis is a process of measuring and analyzing the harmonic content of the electrical current. Harmonic analysis can be used to identify the sources of harmonics and to determine the appropriate mitigation techniques. In summary, harmonics can cause a variety of problems in electrical systems. By understanding the sources of harmonics and implementing appropriate mitigation techniques, you can help to ensure the reliable and efficient operation of electrical equipment. In conclusion, understanding the fundamental relationships between voltage levels like 120 volts and 208 volts, the intricacies of grounding and bonding, and the potential impact of harmonics are all vital for anyone involved in electrical work. Safe and efficient electrical systems rely on this comprehensive understanding alongside adherence to the NEC and other relevant codes and standards. Always consult with qualified professionals for any electrical work to ensure safety and compliance.